Hello, my name is Sean Kelly, and I will provide an overview of our paper, Feature Instability Search for Multi Way Explainability. We will first look at the current state of explainable AI. Then I will outline feature instability, a novel measure of post hoc explainability for black box functions, a ground truth model to assess accuracy of XAI on this measure, and a search model optimized for feature instability. XAI can be defined as how or why a machine learning model, or AI agent, gives a specific output, with the goal of providing utility to human end users of the models. High predictive performance is sometimes enough. However, sometimes asking why predictions were made is more important. For instance, when used in medical diagnosis or domains highly impacted by bias and regulations, such as the case where credit lines are rejected due to protected characteristics or assessing self-driving safety. XAI can be classified using a hierarchy. Local interpretability is concerned with why a particular set of inputs gives a particular output, whereas global methods explain holistic model behavior. Methods such as linear regressions and decision trees are inherently explainable as their respective zero-shot and learned structures directly interpretable. Model-agnostic methods are performed post hoc over a trained model by analyzing changes in model output given changes in input, including, for example, counterfactuals, feature importance, saliency, and feature attribution. However, there are many quantitative measures of explainability with inconsistent implementations. XAI is difficult as deep neural networks use high-dimensional space to map patterns between inputs and outputs, which humans can't visually comprehend. Current methods don't have a direct intuitive relation to explainability, making ground truth evaluation especially difficult. Feature attribution methods attempt to explain deep neural networks through local linear function approximation, which ignores the complex nonlinear interactions between features. We propose the concept of feature instability as a measure of explainability for the output of a model. Given the simple two-dimensional space displayed on the left, feature instability is defined as the magnitude that a combination of features must be perturbed to reach the decision boundary. Intuitively, the most unstable features are those that, when perturbed, lead to the greatest rate of change in model output and are therefore most important in explaining the prediction. Conversely, features that don't change the model output when changed are not important. A synthetic model with predetermined ground truth multi-way feature explainability can be created to evaluate explainability frameworks. This decision space shows a sample of the model's predictions with given outputs. Feature interaction clusters distances are defined by a minimum cluster with a growth function that increases the distance from the source input and the prediction to be explained of incrementally distant clusters. This model provides a predetermined ranking of the k most unstable feature interaction clusters with known magnitudes of feature instability, which can be explained via XAI methods. DFEST is an informed feature stability descent search algorithm with the objective of quantifying multi-way feature instability or importance for a given prediction. Or more formally, it is a binary prediction XAI method using local post hoc interpretability and feature perturbation. Due to the exponentially scaling decision space, DFEST first identifies heuristics of feature interaction clusters via the generation of an even distribution of points on the surface of an n-sphere over the decision space of the model. Secondly, an informed cluster search is implemented as A-star search to locally search for a decision boundary toward the source input to be explained, from a priority queue of feature interaction clusters with non-minimum feature instability, which functions as gradient descent with restarts. DFEST returned the 50 most unstable feature interaction clusters from a model trained to predict malignant and benign tumors, given tabular input data. Green and red boxes denote positive and negative feature interactions, while white boxes denote an absence from the cluster. It is clear that clusters with the highest instability tend to have the same core unstable features, in other words, the most unstable features in each cluster. A feature importance ranking function was created capable of comparing one-way feature explainability frameworks such as LIME and SHAP to more expressive frameworks like DFEST. Prior to being deployed in the wild on a trained model with unknown parameters, it's important to benchmark the performance of XAI methods on a ground truth measure. Despite challenges with scaling constraints, DFEST outperformed the state-of-the-art XAI method, LIME, on the synthetic ground truth model from low to high dimensional input.